Light passes through materials whose atoms absorb the energy and immediately re-emit it as light. Light is energy carried in electromagnetic waves. It's generated by vibrating electric charges. When light strikes matter, electrons in the matter are forced into vibration. Just like a sound wave can force a sound receiver into vibration. Here in the image you'll see two tuning forks that are these orange things right here. If this tuning fork is hit, then the vibrations of the air are going to come over here and vibrate this tuning fork with the same frequency. So just like that can happen, this can also happen when there's a light wave that can force charged particles into vibrations. Here it is in motion. Exactly how a material responds to light depends on the frequency of light and the natural frequency of electrons in the material. All objects will vibrate with a frequency that is natural to itself. So the frequency that is easiest for it to begin this moving back and forth. Visible light vibrates at a very high rate, more than 100 trillion times per second. That is 10 to the 14th hertz, one with 15 zeros behind it. To respond to these ultra-fast vibrations, a particle has to have very little inertia. Remember, inertia is the resistance to change its motion. Electrons, with their small mass, can vibrate very fast. Materials that transmit light are transparent. Glass and water are transparent. Materials that are springy or elastic respond to more vibrations at some frequencies than others. The natural vibration frequencies of an electron depends on how strongly it is attached to a nearby nucleus. So we have this image here which has the nucleus and then the electrons orbiting the nucleus, like with the Bohr model. The electrons of atoms in glass can be imagined to be bound to an atomic nucleus as if connected by springs. So these electrons are springing, they're bouncing, they're oscillating, going back and forth like this at different frequencies. Electrons in glass have a natural vibration frequency in the ultraviolet range. In ultraviolet light, resonance, or that forced vibrations, just like with the tuning fork, occurs as the wave builds a large vibration between the electron and the nucleus. The energy received by the atom can either be passed to neighboring atoms by collisions or sent off as light. If ultraviolet light interacts with an atom that has the same natural frequency, the vibration amplitude is unusually large. So if the natural frequency is like this, and it matches the natural frequency of ultraviolet light, if that ultraviolet light comes in contact with that thing that has the natural frequency that's the same exact frequency, it's happening at the same exact time, then the combined vibration amplitude, the amount that it vibrates, is really big. The atom typically holds on to this energy for 1 million vibrations, so which happens in a really short amount of time, 100 millionths of a second. During this time, the atom makes as many collisions with other atoms and gives up its energy in the form of heat, that thermal energy. That is why glass is not transparent to ultraviolet. So ultraviolet can't go through glass because the atoms are colliding and not able to get through. So that energy just gets transferred out as thermal energy. When the electromagnetic wave has a lower frequency than ultraviolet, like visible light, the electrons are forced into vibration with smaller amplitudes. The atom holds the energy for less time with less chance of collision with neighboring atoms. Less energy is transferred as heat. The energy of the vibrating electrons is re-emitted as transmitted light. Glass is transparent to all the frequencies of visible light. The frequency of the re-emitted light is identical to that of the light produced with the vibration to begin with. The main difference is a slight time delay between absorption and re-emission. This time delay results in a lower average speed of light through a transparent material. So we've talked about the speed of light being found and being constant in a vacuum where there's no air. But when light hits a transparent material and it's going to go through that material, as the light is traveling through the material, the speed of that light starts to slow down. A light wave incident upon a pane of glass sets up vibrations in the atom. Because of the time delay between absorptions and re-emissions, the average speed of light in glass is less than the speed of light, which we use the variable lowercase c to show the speed of light. This image here shows these three circles. Imagine the circles coming in, or being the atoms of the light. And as the light comes into the glass, it's going to hit the atom of the glass. The atom of the glass is going to eat it up, burp it out, and it's going to collide with the next atom, which is going to eat it up, and then burp it out, and then collide with the next atom, which will then eat it up, and then burp it out outside of the glass. And this is just showing you, as light travels through material, it's colliding with these atoms, so that takes some extra time. So the speed of that light slows down. In a vacuum, the speed of light is a constant 300,000 kilometers per second. We call this speed of light c. Light travels slightly less than c in the atmosphere, but the speed is usually rounded to just c. So similar to acceleration due to gravity being constant, even though it's not, but we kind of round it to 9.8 or 10, we're doing the same thing here. It's not exactly 300,000 kilometers, but it's close enough, we're going to just call it c. In water, light travels 75% of c, so we would say the speed of light in water is 0.75 c. In glass, light travels about 67% of the speed of light, depending on the glass type. In a diamond, it only travels at 40% the speed of light. When light emerges from these materials into air, it travels at its original speed, c. This is the, that way, speed limit. It's known as the cosmic speed limit. Nothing can go faster than the speed of light. If things start going faster than the speed of light, then physics starts breaking down. And after hundreds of years of experience, this is known to be true and still holds up today.